OpenDS is open source software. It's implemented in Java, therefore it's platform independent, and it consists mainly of two components. One is the simulator itself, and the other one is the analyzer tool. Both tools are based on the JMonkey engine, which is a well-known graphics or game engine in the Java developer community. It's a high-performance scene graph-based graphics API and uses the lightweight Java game library for rendering. This game library supports OpenGL 2.0. As the physics simulation, it's built on the bullet physics library, which allows mesh-accurate collision shapes and lets the user experience different forces such as acceleration, friction, torque, gravity, and centrifugal forces, just to name a few. Inside this toolkit, we have a toolkit for generation of graphical user interfaces. So this is called Nifty GUI. It allows the user to create drop-down menus, checkboxes, other panels, whatever you have in typical graphical user interfaces, but you have it within the rendering screen. This is what you see when you start a software, for example, when you select a driving task. And the JMonkey engine provides basic audio support and supports several common 3D model formats. To mention is the wavefront object. You can directly import wavefront objects, Ogre XML, and native Blender files. And as well, you can import every files you have in Blender with the Ogre XML exporter. Here's just an overview about the architecture. I don't want to go into too much detail at that point, as we will see some of these concepts later on. I just go a little bit through these boxes in this diagram. From left to right, we have input handling. We can attach keyboard, mouse, and of course game controllers like steering wheel, joystick. But also we have the possibility to attach a CAN server. So this is an external application we used in our lab to connect to Smart. So this brand Smart car. And there we grab data from the CAN bus, which is sent via a socket connection directly into the simulator. So you can sit in your real car, turn the steering wheel, and move through the virtual reality. We have camera controller where you can select between different camera settings. In the past, we also had experience with external visualization. I don't want to go into too much into detail on that part. We have basic audio support. It's really very basic. This is maybe something for the developer workshop. We would like to enhance the audio system, and currently we just lay back the noise from the engine, which is not that sophisticated. We have an HMI controller, so we have experience with sending presentation to the user. This has been used in the past with a system from the SimTD project. SimTD is a German project which is called Safe Intelligent Mobility Test Field Germany, and I was involved in this project. We implemented the HMI of more than 25 use cases. You can imagine this was a screen inside your car, and when you were approaching to maybe to a traffic light, you get some information about the upcoming traffic light phases. We had in-car information about the car in front of you. If the car was braking, you would be warned, and all this was possible with car-to-X and car-to-car, car-to-infrastructure communication. So we had this screen. The HMI was implemented at DFKI, and we used our simulator to evaluate the HMI. So we attached it to OpenDS, and we re-implemented traffic lights at some intersections. And when we were driving in our simulator, approaching to this traffic light, the Flash GUI was showing up these presentation tasks, how long the traffic light will be red, or if there was a danger warning if a broken down vehicle was in front of you. Furthermore, we have traffic light control. We will see this later on. For this reason, we have a connection to Sumo, to the traffic simulator. We can grab this data of certain traffic light states from Sumo and directly send them to our simulator. Furthermore, we have traffic, and we are able to perform reaction measurements, which can be visualized as a Jasper report after the trial. The whole time we can log all the data, which is stored to your hard drive disk in some text file. This can then be reopened by our driver analyzer, which is more or less built on the same system. They're sharing classes, so it's one big architecture, you could say. And you get this driving data into our analyzer, where you can visualize it again. You can process a deviation from some idea line you have defined before. Okay, let's see now some of the features. Here are some screenshots of what I've already mentioned from our SimTT GUI. So the screenshots in the upper half. On the left, you see the broken vehicle. So this is a local danger warning. In that case, you were approaching to a broken down vehicle in our simulator, and this HMI was showing distance with a progress bar that was decreasing, and of course, the distance in meters with an icon and also in text form. On the right, the same thing for the traffic light phase assistant, where you will be noticed how long the traffic light will be red, or if it's in the case it's green, what recommended speed you should drive at. Our simulator comes with some sample tracks, and on request, we also provide standardized driving tasks. On the lower left screenshot, you see the country task. Tomorrow morning, we will have more details about this task. I can say it's without real car driving, so it's somehow different. You just have to control bars there. In the screenshot in the center, you see a model, I would say, of the second generation. In the meanwhile, we have already reached the third generation. And on the very right picture, you can see an image of our lab in Saarbrücken on the campus of the Saarland University, where we have attached a smart car I mentioned. We get the CAN data there, and we are able to sit in this car in front of the screen and drive through the virtual environment. You can see, maybe in this picture, here we have a three-parted screen with 3 projector setup, and our software would even support more screens if your graphics hardware does support that. Yeah, I already mentioned in our traffic light simulation, we can attach Sumo. So this is the bullet point interactive external control. This doesn't necessarily need to be external software. You could even give manual external instructions. So if you see your participant driving, you can trigger a red light per button, if you like. We have predefined cycles. This is, I would say, the usual case. And we have red light or green light on approach in order to trigger scenarios where the driver will have to decide, will I stop before the traffic light or will I make it? For our traffic simulation, you see the 3 screenshots in the lower half. You can place waypoints. These would be the red boxes you could see there, and make the vehicle follow those. So there's a blue line connecting these boxes, and the vehicle will follow. You can even assign speeds and acceleration values to your vehicle for these sections in order to follow these lines or to obey to speed limits in some sections. Furthermore, the traffic obeys to traffic lights. So whenever a red traffic light is close to the car, it will stop. And also it keeps the safety distance to you and other traffic vehicles. Yeah, then we have special weather conditions. We have rain, snow, and fog. We could also drive at night. We could reduce light and maybe apply a stars and moonshine texture as skybox. For that case, we would have a light model in all the vehicles. We have headlight, we have brake light, and we have a turn signal for them. All the driving cars are equipped with a realistic engine and transmission model. This could be used in order to compute fuel consumption for good drive tasks. We have event-based control of all the scene objects. As already mentioned, we can trigger traffic lights to turn to red or turn to green. We can make obstacles appear or move the traffic to some position in 3D space. In the picture on the right, we could imagine we are approaching to the stop sign and we want to make traffic appear at the intersection that's moving from the right to the left. All the scene and interaction can be configured via XML files, and you won't need any programming skills at that point. Here's just a short list of the available events. Maybe I just name a few. We have send message event where you could show some instructions to the participant. All the events can be, by the way, can be triggered with key press or when the driving car reaches a certain position. Then you could show maybe instruction screen. You can make objects appear. This would be the manipulate object event. You can show pictures in the screen, maybe a map for navigation or something like that. You can of course start or stop the recording for your analyzer. The reset car event would be used for placing traffic anywhere. No, stop. The move traffic would be used for placing traffic. Reset car is placing your own car. Maybe if you want to set it to start position, or if you have a second drive, you could use this trigger to place it at a second position. Here there's some other events that might be helpful. Play sound, maybe for some special driving tasks. And all these events are equipped with two further parameters that every event has, which are called delay and repeat. So you could make an event to start with a delay, and you can set a maximum number how often an event could be repeated. If this number is 0, there is no limit at all. On the right, you see just two examples where we have in the upper half an object manipulation, and actually we set it to a new position. So there are the parameters. You can set translation and 3 numerical values, and that means the object that is called roadwork sign in that case will be placed to another position as soon as the user presses the X key. I don't know if this is a sensible trigger in this condition, but it's for demonstration, I think, just okay. More realistic trigger would be in the lower half, where we are reaching a finish line and the user is prompted a message that he has reached the finish line, and at the same time a recording will be stopped. Yeah, this is an important topic. We were often asked for a driving task editor, but we no longer support it. This was just a master thesis, and it's a little bit outdated by now. It's too much effort to have two systems in parallel implementing. So the simulator developed further, and yes, Christian just wants to add something
yes,
here?
I want to comment on this. Many things that we do in OpenDS are theses, and we work a lot with students, and it's not only the problem that it was only a massive thesis. We started this project of the driving task editor say rather early in the project, when we did not really know which direction we would go, and this Ottavio here, who did this, did a great job, and we don't want to really not respect his work in his thesis, but meanwhile we did a lot of other design choices which made other solutions for driving task editing more reasonable and better integrated into the workflow of OpenDS, and therefore we decided to not go this path anymore. We even found out that after a while we had a hard time using this tool ourselves, and we could not even imagine to explain our users how to use it, and therefore forget about the driving task editor as it was. We will present other ways to create models during this tutorial.
Okay, thank you, Christian. As you already mentioned, we have alternatives, and these are, we use City Engine. This is something we did already before for the generation of models. And at the moment, we are doing manually the placement of objects in our world. This could be done using some 3D graphic software, for example, Blender. You could load a model and place some traffic lights in there. So you have the position and you can finish your model in Blender. There's another alternative, which is part of the upcoming release, and I will show you in the demonstration later on. That's called Object Locator. So you can just drive through the model, and wherever you want to stop, and you can just drop a traffic sign at that position, and then you go on for the next position where you can place the next sign, the next car, whatever you like in your model. And still under development, or I would say even not really started, is the plan to have an OpenDS exporter for City Engine. So we're thinking of integration of such an exporter into City Engine in order to not just export raw 3D models, but also the semantic information we have in City Engine. For City Engine, it's possible to open OpenStreetMap data, and there you have many information about the road, about the buildings, and we could make use of this semantic information inside our simulator. We would know what objects are buildings, what would be road signs, what would be streets, and using this information, we could set up a whole driving environment with little effort. And the fourth bullet point here would be the GenXDS, which is used for experimental setups. So yeah, this slide is about GenXDS. We will have more details, I think so, tomorrow by Simon Lindner. This is also a non-graphical task editor that could be used to create massive driving task data. You see a screenshot on the left where you can set up some different parameters. For example, we used it only for one case till now, where we had a multi-lane road. It was a straight road, and you could specify what distances certain events may occur along the route. And in our specific case, we implemented these road sign gantries, you can see here. And by specifying our parameters, you could set up the distances between road sign gantries, how many you would like to have, and something about the balancing of events that were shown on these secondary sites. So we want to add even more tasks to make a more general software here. You could think of a generator for even lane change drives. And there's high potential in this editor. I think development is planned to start in the next half a year. Okay, so we had now these possibilities to start to create a driving task. We can load this driving task, perform our drive, and afterwards we can have the analyzer to replay this drive. So from the recorded car data, you can visualize the path you have driven. In this image below, it would be this yellow line, if you can see this. And as well, this analyzer is able to compute a deviation from a given normative track. So imagine you have some path you want the driver to follow through your city model. You could implement this normative track. It's shown here as this blue line, and the software is able to compute deviation here and visualize it as this red area. The smaller the area, the better the driver performed, and this gives us a driver performance indicator. But not just deviation could be visualized in that way. On the left, you see an example output from this country task. This is where you could manipulate these bars, and the deviation in that case could also be shown as such a diagram. You see this chart in the lower half is red at some positions. This is because we are able to set up a threshold which we tolerate, and whenever the driver exceeds distance, we can visualize this in the red color, for example. As well, we have some bar charts here for presentation of reaction times. Yes, here's again screenshots of the two tasks I've already mentioned, the continuous tracking and reaction task, country task. And what we will see in more detail tomorrow, the 3-vehicle Latone task, where you are the car in the center and you have to follow the car in front of you, keep the safety distance, keep your position in the lane, and by the way, you will also have to react to some events that will randomly occur. Yeah, this will be a report of this second task. It's a little bit more detailed. We have distance to keep, we have to keep our position in the lane, and also some reaction time. We will see more details tomorrow. Now let's come back to the upcoming release. Those who are here today in Eindhoven, you will find a USB flash drive in front of you, and on this drive you will find a preview version of our simulator. All the others will have to wait till next month when we have the official release. For those at home, I will give you a link to these files for the tutorials, as we will need the source code there, and you later on can download it from our website from a special area, non-public area. Yeah. Okay, let's now look at the changelog from our first release to now. The most important change is that we updated the internal game engine. So I think the last release was built on the JMonkey engine, which was by now more than 1 year old. So it's a large gap until today. And this allows us lots of features that have been implemented in the JMonkey engine to work on with OpenDS. So one thing is shadow rendering. We have a more sophisticated shadow renderer as it was possible before. There's several filters now available. you can see in the first image on the right by this nice fort. There's a shadow below now. We also have now terrain into our simulator. You can use simple height maps, which are a grayscale texture. It's the darker the color, the lower is the terrain, and you can place white spots in this height map, which shows where the peaks of maybe some mountains will be. I will show you later on an example when we have the demonstration of the terrain. Then you will see how such a height map looks like. Another important point is the new driving task already introduced, and we will have more details tomorrow. We now have side view mirrors. By now we only had this rear view mirror. Now we have one on the left and on the right. And all the mirrors can be adjusted in the settings, so you can adjust the size, the position, and also the angle of these mirrors. We will have new models, a new outside camera view, and as already mentioned, this tool Object Locator, where you can easily position traffic signs, cars, whatever you want to have in the scenery. There are two new trigger events. One is called speed control trigger, which could be used to have a look at the current speed in a certain position. So imagine the car is driving through a section where you're only allowed to drive at 30 kilometers per hour, and you can, you would say in real traffic it would be a radar, and you could check the speed of the driver. If he exceeded the speed, some marks will be recorded. The other event is the placement of a navigation screen. As you might see in the screenshots, the lower screenshot on the left. It's really tiny here, but we will see it running in our demonstration, where we have very basic navigation screens. The next point was a request of our users, as they had sometimes problems attaching game controllers, and now we offer possibility to have a dump of your joystick assignments, of your steering wheel assignments, where the axes are labeled, and you have the IDs to these labels, so it's easier to assign the gas pedal, the brake pedal, or the steering axis to your steering wheel. Yes, and also minor bug fixes have been performed. One you might notice when you run the new version for the first time, the scrolling is now fixed when you select the driving task and you use your mouse wheel there. Okay, now let's move on to demonstration. So I just started the simulator in a smaller window because the first demonstration is about the integration of the HMI. This is still an older demonstration in the first half, so you might see things you could also do with the first release. And in the second half of the demonstration, I show you the innovations that are available with the next release. So here we have our traffic light face assistant in action. You can approach to a traffic light and you see it synchronized with the HMI output, which was used in our project SimTV. I'm approaching to the traffic light and the HMI shows that the light for turning left will be red for another 3 seconds now. And now it will switch to green. And as we are going to drive straight ahead. We just have a little bit to wait. I can also use the steering wheel, which is attached here to my car. Here's traffic on the roads. So we will now drive through the road till the very end of the street. Might not get too fast. Could slow down. There will be a traffic light at the end. And then we turn left. Ooh. I can go to the left. Brake should work. The brake. Okay.
I found the brake. So that's
okay. So we can now go on driving, and we currently are performing a recording of this drive, and we will see in the analyzer after that drive how Christian performed. Just go on a little bit till the end. There will be a trigger, a message showing up when you reach the end. This has happened now. So let's see. Here's just a collection of all the drives I performed before. Go to the newest. And now we should see the driven line. There should be a yellow line visible that Christian has used to drive through this model. So we can go on. By the way, for those people joining us from the remote computer, we know that there's only a limited frame rate available, as I think the updates of my screen are only 1 or 2 per second, so it might be not that nice to view from home. Now let's go to the top view. You see this blue line. This is a reference line that has been defined for this model, and the yellow one is where Christian was driving. You see there's some deviation. It's getting more after the traffic light. Yes, I had to manually do this, and there are 2 ways. You could use a 3D modeling tool where you can set these waypoints. You see, it's for here, for example, in that position. There you see these there are edges that are between these waypoints. The more waypoints you have, the better it would be. And the other thing you could do, you could use a driving car and record the first drive and use this as waypoints. So what we do here, you see the yellow line has been created in this way, but you could also use the data from the yellow line to say this is my ideal line for further drives.
You need a better driver than I am.
Yeah, here we had a very large deviation, and okay. Yes, so maybe. So the next one is a demonstration of the continuous reaction and continuous tracking and reaction task, country task. Somehow different from driving. Doesn't work. You have to really spin the wheel here. So Christian is now controlling this blue bar. The yellow one is moving randomly to any position, and he has to keep the distance between both bars as little as possible. And you see this traffic light. They are red. Yes, I know it's not configured properly for this task. I know. we'll really have to turn it. So we can decrease and increase the sensitivity for each task separately. And you see these lights appearing, and you would have to react to the red light and green light separately. When we stop this task, we will get.
We will come back to this.
Yes, we will come back in more detail tomorrow. So here you would see how Christian performed the steering deviation. So you were far off, and we said tolerated area here is 1 meter to the left, 1 meter to the right, which is exactly before you have a gap between two bars. And as he has not reacted, you have the maximum reaction time everywhere.
It is different from the lane change task.
Just a few words about it. We also have lane change, a replicate of lane change in OpenDS, but we decided to develop this content task for several reasons. The first reason is it has a higher time resolution in time for your feedback than lane change has, but we will have a separate session tomorrow about these driving tasks, and it's different from lane change tasks in a few respects.
Okay, the next task is outside of our city models, but has also been created with this tool, what's called City Engine. Even if there is no city, we can also model some terrain with this software. We have this road implemented with some signs. You saw this bus driving by. Yeah, rather unspectacular. We use this normally to show the physics, as you can drive up the hills, but there are currently no hills. At the very end, I know there's a very steep inclination. Okay, we'll see maybe a better demonstration of that in our terrain model, which belongs to the new release. So now we are back to the first model, and the only difference is we have now switched on some weather conditions. It should be foggy and snowing in the next model. Heavy snow. So this was already part of the first release, and will be something we are going to use today in the next tutorial after this session. So we will set up our city, and we will also have some weather conditions in there. Oh, there's somebody disobeying the traffic light there. Now we are getting to the demo for the next release. I'm not sure what the first one is about. We will have to wait. Yes, this is a demonstration of our navigation screen. So in the lower left, you not completely. So what's new is this small screen in the lower left. So we have now we can manipulate pictures that are shown on this parallel node. So it's in the scene actually. There's a picture shown which indicates you now to drive right. And what Christian mentioned that it was available already in the first release is what we will see next. That here's a trigger placed at close to this sign, which makes traffic appear from from the street in the background.
To my excuse, it's very difficult to drive when on this very weird angle.
So Christian now can maybe place this car in front of the other one and stop there. You have to go more to the left, otherwise it will drive by. We have really blocked the road. And the other vehicle should notice that we are here and should stop there. So I show it from the top-down view, and Christian now can drive a little backward. I just change to the reverse gear. Doesn't work? Yeah, just press the pedal. Okay, now you make more room, and the car will fill the gap. And as soon as there's enough space, it will pass by. Oh, this was the camera view from a very far point. So now we are back here, and we can just follow the drive. We are advised to drive straight ahead at the next intersection. I just have to change again to the drive forward. Yeah. And now turn right, and then I think we already reached the end of the model and the end of our navigation instructions. So it's a really small model here. The next one is the demonstration of terrain. For that reason, I just switched to this height map I promised to show. So height map looks like that. It's a square of 1024 times 1024 pixels, and it shows you this transition from black into from black via gray into these white spots. And the brighter the image is, the higher the mountains will be. So you could imagine if you drive around a little bit in this model, there should be some hills behind you. So make a U-turn. Yeah, you can see there are some hills that have been generated by using this height map. They're so steep you can't even get up here. You can see this is a square. It's not very large, this model, and you can use this height map and some parameters to define the scale in the up direction, how high these mountains will be. So what will be the maximum of a peak? Oh, no damage. But it's not all, but not just this height map, which makes this terrain generation very simple. You use also an alpha map. So take them both next to each other. You see there, if you overlap both of them, they somehow match, as this alpha map describes the textures that have to be applied on your terrain. So all the green areas are used to have this sandy or rocky texture where the mountains are very high. The grass, I think, is the red part, and this cobblestone path is just this blue part. So all you would have to do is just, you need these two images, and you're just done. You have your terrain that has been implemented, has been visualized according to these maps. Terrain procession is really fast. You can see we even have very high frame rates at that computer, more than 700 frames per second. So I think for the next model, Christian is maybe the part who should take over, as the model is something he has implemented. It shows the campus of the Saarland University in Saarbrücken, and is what I would call a model of the third generation already. Yeah, it's a really large model, so it takes some time. And I pass the microphone over to Christian.
Yeah, well, this is still under development, so I have to comment on that. So it's not the way our campus looks like. This looks like our campus after, well, some next World War or something like that. But you should look at it from a perspective of engineering. So we made this using 3D laser scanners, and we scanned this entire thing. You can tell from looking at the roof shapes of that building that this was recorded from the ground, because the windows on the roof throw shadow to back, so that's where the laser light was shadowed out. And also the windows are problematic here because windows are transparent, and transparency is not captured by the laser light, and that's why the windows look especially rough and need some more post-processing. But we are already kind of satisfied with how far we got with in terms of the actual reconstruction of the building. So the benefit we have here is, I have to say that the point cloud was not complete. So there was also the corners of these models are really also not represented in the point cloud. So the reconstruction was pretty good at that point. Those of you who know the university campus will certainly recognize this torque here, the sculpture, and the benefit that we have here is, first of all, this model is auto-generated. We don't need to model this by hand. Second is we have realistic textures, colors. We even have the exact asphalt and of colors, and also the shapes of the roads. And it's compared to a model that you build up from some geometry data. It contains a lot more details, and it would be useful in situations where you really want to have something that people recognize. It's really an area that where people where you want to have a high recognizability of the scene. And again, just for the records, this is not complete, so we are not going to deliver this in this condition. We are still working on it, and once it is ready, you will see the end result.
Yes, I would just like to add, this model has to be optimized, as it's really complex, and you could see this that we cannot move that smoothly through this model. We have physics computation in use, so this is what it partially makes it that complex. I can collide with the objects, and it's so complex. You can see there are plenty of triangles, even more than necessary, and we would have to reduce them to have a good physics computation here. So the next model, no, not this one, is some excerpt of the large campus model, but with another technique. So we show the torque now again, and I just hand over again.
So that is part of the same scene. We cut out a small piece of the campus scene in this model, and what makes this technique interesting for our users is that we actually did this on photo recap. So this is not we did not use the the laser scanning data, we did this on a photo recap technique. So that means that we could even create these scenes by a 3D recap based on photos, and this is it's also a different surface reconstruction algorithm used here. That's why it looks different from the one we had before. You can even see that this algorithm tries to close the shapes that it receives. When you go on the backside of this building, you see that it closed the surface, although there is essentially nothing to be closed there. It always tries to create a closed surface, and this model is already a little bit has a little more or less polygons than the ones we had before, and we're still trying to find an optimal way of this like recap based model generation.
Okay, next one is a small preview of the 3-week platoon task I mentioned earlier. It's just for demonstration here, as we're going to show the real task during the break on the JDOM. So you can have take a seat there and have a test on your own. So in general, you're part of this platoon, you're in the middle, you're following the car in front of you. Your task is to keep some safety distance, to keep the position in the lane, which is better done with the steering wheel, of course. And you will have to react to some events. Maybe the car is braking, it's not braking, and sometimes the car behind us will turn on the turn signal, but I think more details will already be provided tomorrow. Okay, so this would be our output from that task, and I think there is just one more. Then we are through with the demo and can start for the coffee break. This is also a new feature of the next release, which we call the object locator. Now you can see we are inside our driving car, and if I like to place some object, let's say I take a sign I want to have here. No, there's no band. Yeah, let's say we want tomorrow start road works here. We just go there, place it, can move it to our final position and just drop it and drive on, and this, the sign will stay there. There. Place the speed limit here. Priority road. Let's assume that's a dead-end street. Oh, just was too fast. So there's a list which can be easily specified as a text file. You just have to specify the path to this model, and then you can use your keyboard to go through this list, select the right one and position it, and if you found the position, then you can just place it there and go on to the next position. So this could be used to generate simple models. So we mentioned we don't use the driving task editor anymore, and so in this way you could place these signs. But you could also replace them by cars, static cars that are parking at the side of the road, or you can also use this for placing waypoints your traffic should drive by later on. Okay, so this was all of our demonstration. Now you have the chance to use our JDOM and to refresh yourself with a cup of coffee.